and pick up where we left off. Let's see here. If I told you I had a sample of material, right? 16, we'll do 32. 32 grams of oxygen in this sample. 4 grams of hydrogen in this sample. Okay? And I want to know what is the empirical formula. Empirical formula. Do you remember what the empirical formula means? Okay, it's the ratio of atoms, and it's not the mass ratio, right? But it's the ratio of atoms in terms of moles of material, right? In terms of moles of material. So, how would I go about answering this question? What would I do? I need to find the moles. Is that what you said? Find the moles, what meaning? Find the moles of like the different components, the different elements. So, maybe if I were to set up my system here, what would I put to the right of my equal sign? Moles of oxygen, is that what I heard? Moles of oxygen, and then I'd want another one where I had what? Moles of hydrogen. Right? Because if I know the number of moles of oxygen and hydrogen relative to each other in this sample, I would be able to get close to this empirical formula. Right? Okay. Now, moles of oxygen. Up here, what would I start with then? Grams of oxygen, 32 grams of oxygen. And then down here, I'd have to have grams of oxygen. Up here, where am I trying to go? Moles of oxygen. And that's where I'm ending up, so that's good. Okay. And then over here, what would I start with over here? 4 grams of hydrogen. And then I would go from grams of hydrogen to moles of hydrogen, just like over there. Right? The number, what's the relationship here? What's this business? Grams to moles. Okay, 16 grams of oxygen per mole. How do we get that information? The periodic table. The number on that, below the elements on the periodic table, is the number of grams necessary to get a mole of that material. Right? Very good. So, this looks like I'd get 2. Is everybody comfortable with that? Anybody want to talk about how I got a 2 there? Raise your hand. Otherwise, we'll move on to this one. What's the relationship here? 1.001 or whatever it is, grams for every 1 mole. Very good. So I have 4 moles of hydrogen. So now I can use this 2 and this 4 where? As the subscripts in my empirical formula. H4O2, right? And then that is not quite the empirical formula. How do I know this is not the empirical formula? Yeah, you need the simplest whole number ratio to have the empirical formula, right? So that when this empirical formula here is H2O, right? That's our empirical formula. Okay? This was the data that we started with, right? Does that make sense? What is the percentage of oxygen in this sample? So let me draw a little pile so that we can kind of think about it. You know, room temperature, this is going to be water, a liquid, but just for thinking purposes, there's a little pile of my material. 32 grams of that and 4 grams of that. Okay? What percentage of that material is oxygen? How do we find that out? All right, the total, 36, and then put the 32 over the 36, right? So could somebody do that for us in their calculator real quick? As soon as you get it, just let me know. What's that? Okay, so 88.8% oxygen. And the other one, hydrogen? 11.2? What's that? 4 divided by 36, is that right, or did I do that wrong? Okay, or 11.1, thereabouts. Percent hydrogen. Now, what if we hadn't been given this information? What if we hadn't been given this? Maybe they only told us this, and they asked us, what is the empirical formula? Could we still answer that question? We should be able to, because we got this simply from that, right? But maybe our brains aren't quite wired to know what this means.
So we can say that we have 100 grams like total, and so we can apply the 88.
Make them grams instead of percentages. Very good. So I'm going to draw a little bit bigger pile this time and say here's 100 grams of whatever this stuff is. And then I can just change these 88.8 to grams and 11.1 to grams. And then theoretically, if I put the 88 grams, because this is oxygen, 88.8 here, what's 88.8 divided by 16? 5.55. So I'm going to try that. I'm going to say, okay, HX, OY, O is 5.55. Now let's take the 11.1 into here, divide by 1 times by 1. That's going to be H 11.1. All right. Is everybody okay with these numbers? See where I've gotten them? Anybody want to talk about those? Question? You sure? Anybody else question for sure? No questions? So how do I simplify this then? Did I do this right? I'm supposed to be able to divide all of these by what? 11.1? Oh, no, sorry, 5.5. 5.55. And that makes it H. This is 1. Does this end up being 2 here? Okay. So, from either information about the masses or information in percentage, because percentage really is about the masses, it's just assuming a 100-gram sample, right? So from either of those sets of information, so it's really the same kind of information, isn't it? It's all about mass, whether it's given to us in actual masses or percentages, which we can quickly turn into actual masses of a 100-gram sample, right? From that data, we can identify the what? What do we call this thing? Empirical formula. Very good. Now, empirical formula. The empirical formula is not necessarily what we call the molecular formula of a given compound, right? So remember we gave the example of this compound. What is this compound supposed to represent for us? Glucose or sugar, right? So this compound here, glucose, has a molecular formula as shown here, but its empirical formula would have to be reduced down to what? Yeah, CH2O. Let me scoot that down a little bit. So how did we get from the molecular formula to to the empirical formula? What did we have to do? Or maybe the other way around. How do we go from the empirical formula to the molecular formula in this case? Yeah, we multiply all those values by 6. So there's a multiplier, we say, right? Some value that you're going to multiply the subscripts by to get up to the molecular formula from the empirical formula. So I'm going to remind us, this is the empirical formula, this is the molecular formula, and that there's some multiplier between them. Okay? Now, if you think of the mass of something that would have this chemical formula, the empirical mass, which is basically the mass of the empirical formula, right? What is the empirical mass here? Does anybody have any? Can somebody add that up for us? We got a 12, we got a 16, and we got 2. What is it? 32? No. 40? 30. Oh, great. 30. So the empirical mass, all right, I'll put an equal sign here. The empirical mass equals 30, right? The molecular mass is going to relate to the empirical mass the same way the empirical formula relates to the molecular formula, right? So I'm going to have a multiplier in between here. What does it look like the multiplier is going to be? It's going to be 6, right? So that tells us that the molecular mass is 180. Is everybody okay with that business? So when you are given information about masses of material, either in percentages or straight information about mass, we can get to empirical formula, and that's wonderful. But we really want to get to molecular formula, huh? We want to know exactly how many of those different elements there are in one unit of that stuff, right? To get there, we need to have information about the molecular mass, Because once we have information about the molecular mass, we can get information about the empirical mass because we can get the empirical formula. And that'll allow us to solve for this multiplier, and then we can find out what the molecular formula is. Okay? Let's see if you got it. Let's see if you caught it. I'm going to give you a question here that's going to give us some of the information on that table, but something's missing, and we're going to see if you guys can get it. Okay? So here it is. Here's a chemical, hydrazine. Its empirical formula is NH2. Its molecular mass is 32. And we want to see if you guys can get the molecular formula. The molecular formula. Okay? I'm going to go out so that you can talk to your neighbor because this is neighbor-worthy material. So talk with them. Ask them. If you don't have a neighbor, you got to start finding one, okay? Go. You're so lucky. Was it a wonderful experience?
Even better.
Yeah.
It was amazing
That's wonderful.
and painful.
Yeah, sure.
It was amazing.
That's wonderful. Congratulations. That's so exciting, huh? There's a couple of new people, 3 or 4 new people since I explained how you're supposed to interact with your neighbors. Okay? So I'm going to reteach you how to interact with your neighbors. All right? Oh, you should come up here so you have a neighbor. Come on up here so you have a neighbor. This is how you interact with your neighbor. This is the appropriate way. First of all, you know that you understand this really well. So, you don't want to just say, I know how to do it, don't bother me. But what you do say is you pretend like you don't understand so that you can help the other person. Because the best way for somebody to really learn this is to actually teach it to somebody else. Right? So, what you do is you pretend like you don't understand and say, wow, could you help me out with this? I don't really understand what's going on. Now, why are you doing that? Is it because you're selfish? No, it's because you're what? Selfless. You're trying to help them give you an opportunity to teach you. So even though you understand it very well, you should be kind to your neighbor and say, is there any way you could help me out with this? Now, when somebody says, is there any way you could help me out with this? And you know really well how to do it. The appropriate response is not, yes, the answer is B, right? The appropriate response is recognize that you're going to be kind and pretend like you don't know how to do it very well either. So you're going to say, this is a tough one. I'm not quite sure I know how to do it. Let's see if we can figure it out together. And then you guys go back and forth, teaching each other and learning together. And that will result in the best scenario. All right? Oftentimes, even when people think they know what's going on, they're missing important, deep understanding that we'll be able to develop if they have to teach it to somebody else. Okay? So, if you find yourself in a situation where you're just sitting there not talking to your neighbor because you know everything, you should give them the chance to teach you by saying, is there any way you could help me with this problem? I'm not quite sure what's going on. Okay? Got it? Excellent. Now, did anybody come up with an answer? What'd you get? N2H4? N2H4? Who got that one right? Anybody want to raise your hand and see if you got it right? So, does that mean everybody who didn't raise their hand didn't get it right? Is that true? Who didn't get this one right? Okay, great. So, what we needed to do is we needed to know the multiplier. True? We were given the empirical formula. What was the empirical formula again? NH2. So we were given the empirical formula, but we needed to know the molecular formula. So between the empirical formula and the molecular formula, there's some sort of a multiplier, right? So for example, NH2 was our empirical formula, and we wanted to know I'll write empirical formula here. We want to know the molecular formula. Whoops, supposed to be an equal sign there. Okay? So we know that the empirical formula has to be in ratios of this, right? I mean, if one of the possible answers on your test was N3H2, could that be a molecular formula for this thing? No, because it's not even in the same ratio. We know that it's going to be in the same ratio. We just don't know what the multiplier is. We have to multiply these subscripts by something, but we don't know what it is. And to find that multiplier, we have to identify the mass relationship between the empirical formula, which we call the empirical mass, and the molecular mass. So how do we find the empirical mass if we're just given the empirical formula? The empirical mass is the mass of everything that's in the empirical formula. So this would be 14, 15, and 16, right? 16 altogether. So the empirical mass we now know is 16. How do we find the molecular mass if we don't have the molecular formula? You can't. They have to give it to you, which they did. They gave it to us as 32. Now, that helps us identify the what? The multiplier. The multiplier here is 2. I found that out by taking the 32, dividing it by 16. That means that this multiplier is also 2, and that means that my molecular formula is my empirical formula with the subscripts multiplied by 2. And so that's my molecular formula. Okay? Excellent. So, to get the molecular formula from the empirical formula, you need information about the molecular mass. Any questions about this one up here? Here we go. Here's a substance. We know its percentage of material, right? And I'd like you to use this information about the percentage of the material to identify the empirical formula. Empirical formula. Identify the empirical formula the way we did it up on the board. Don't use this information yet, this 80.06. After you identify the empirical formula, then we're going to use this 80.06. What is this 80.06? It's the molar mass. It's the molar mass. After we get the empirical formula, use the molar mass to identify what the molecular formula is. Okay, yeah?
So we're basing those percentages off of, like, out of 100 grams per sample?
That's right, because percentage will always mean, you could do it just 1 gram. Then you could just do 0.35, 0.05, and 0.59, right? Just the ratio is the same in terms of percentages. So we're identifying now, first, the empirical formula, given information about the mass of the different elements in the sample. Okay, go for it. Talk to your neighbor. Any ideas about this one? Okay. Do you recognize that we're looking for the empirical formula? Right? And the empirical formula is the ratio, right? What are our elements again? Nitrogen, hydrogen, and oxygen. So it's like, whoops, that's supposed to be a Y. These are just unknowns, right? I don't know what those are. Does that make sense? We're looking for the empirical formula. We don't know what those molar ratios are. So what we need to know is how many moles of nitrogen, how many moles of hydrogen, how many moles of oxygen. So we set ourselves up an equal sign where we put to the right, what are we going to put to the right here? What are we going to put to the right of the equal sign? What goes to the right of the equal sign? If we're trying to identify the empirical formula, what goes to the right of the equal sign? What do you mean when you say this one? Nitrogen. So this is the moles of these materials. We need moles. Moles of what? What do we want to do first? Nitrogen. Nitrogen. So we go moles of nitrogen. We're also going to need to solve moles of hydrogen, and we're also going to need moles of oxygen. All right? We need to start with some information here, right? It says 35% nitrogen. You see that? 35%? And you know what percent means? What's percent mean? Percent means out of 100. So when I have a pile of this stuff, if I have 100 grams of the sample, then that means 35 grams is nitrogen. Because they said 35%, where percent means out of 100. So I can put in here grams of nitrogen, like you said, but how many do I put? I put 35 grams of nitrogen. Okay? And then on these ones, how many grams of hydrogen am I going to be able to put? 5.05 grams of hydrogen. Very good. And grams of oxygen? Good. 59.96 grams of oxygen. Very good. Down here, I'm going to need to get rid of my units of grams of nitrogen and go to moles of nitrogen. What value relates grams to moles of nitrogen? That's the periodic table. Do you have your periodic table? There it is. Good. So how many grams of nitrogen are in a mole of nitrogen? 14. 14 grams of nitrogen for every 1 mole of nitrogen. I'm looking for moles of nitrogen, and I end up in moles of nitrogen. So 35 divided by 14 should tell me how many moles of nitrogen. Okay, so try to finish that up for hydrogen and oxygen, and then these will be the moles of the different components. Okay, did you get them? Moles of nitrogen, hydrogen, and oxygen? Did you guys get it? Okay, what's that? Say that again. A shortcut. Using what? The what? So tell us what you did. What did you do?
We got N7 H1.
H over 1? What do you mean?
Nitrogen.
So did you solve for the moles of nitrogen? Okay, here we go. As soon as we see that they're asking for the empirical formula, we have to know we need moles of material. Agreed? We need moles of material. So I'm looking for moles of all of the different elements in my compound so that I can get some sort of a statement, NX, HY, OZ, something like that, right? I want a statement telling me the moles of each of these components. So to solve for the moles of these, I needed to start with the information they gave me. I don't see anything up there that says 35 grams of nitrogen. Why did I choose to use 35 grams of nitrogen to convert to moles here? Did anybody else choose 35 grams of nitrogen here? Why? Why did we choose 35 grams? Okay, if you assume a 100-gram sample, then your percentages are your grams. Okay, very good. All right, so how many moles of nitrogen did anybody get an answer for us? 2.5 moles of nitrogen. How about hydrogen? 5.05. And then oxygen? 3.75. That's a good starting point for us. So nitrogen, 2.5. Hydrogen, 5.05. Oxygen, 3.75. All right. This is not a finished empirical formula, is it? But to get there, I'll force one of them to 0 by, or sorry, one of them to 1 by dividing them, all of them, by the lowest value. So that makes nitrogen 1, hydrogen, looks like it's going to be a 2. Is that true? What's the oxygen turn out to be? 1.5. All right, so I'm not quite there yet, but it looks like I can do what to all of these? Multiply by 2. So N2H4O2. Oh, 3, sorry. 1.5 times 2 is 3. Okay, so that must be my what? Empirical formula to start off with. How do we get to molecular formula? So here's my empirical formula, N2H4O3, and I want to get to my molecular formula, right? How do I get there? What information can I use to get there? The empirical mass, right? Because there's a relationship between the empirical mass and the molecular mass. What is that information? The multiplier. And the empirical mass, they didn't tell us right up there, but the molecular mass is 80.06. How do I identify our empirical mass? That's right. 2 14s, that's 28, plus 4 plus 16, 16, 48, 32, 48. So 28 plus 4 plus 48. Did I do that right? So what's that equal? Is that 80? Okay, so what does that tell us about our molecular formula? It's the same as the empirical formula. So the multiplier here is just 1. So N2H4O3. Right? Yeah.
How do we know which, like for the N, like this, yeah, to go to?
How do we know to go down here? You need a whole number. And 1.5 is not a whole number. Or maybe you were asking, how do you know to multiply by 2?
Yeah.
Because if I look at the ones that aren't the whole number, that one, I see that it's 1.5. And to get that half a whole number, I'll have to multiply by 2. If this was like 1.25, or if one of the values was 1.25, what could you do to multiply, or what could you do to get it a whole number?
It's a quarter, so it's 4.
Yeah, it's a quarter.
Put it in fraction, kind of take the bottom number.
Denominator? Yeah. And if it said like 1.33333, multiply it by 3, right? Because that's a third, right? Very good. And if you're stuck, you just put it in your calculator and try 2 or 3 things, and you'll get there faster than it takes to remember or think. Okay, very good. So then, yeah.
The bottom part is the NM, is that or like mass?
It's molar mass. So molar mass of these different atoms. So it's the same as on the periodic table.
14 grams of N would be 1 mole for that.
That's right. To get 1 mole of nitrogen, you need to weigh out 14 grams. Okay, here it comes. A beautiful question about a controversial pesticide. We want to know the empirical formula of this pesticide given those mass informations. Information about the mass. How are things going? Are you following along okay?
Yeah.
Wonderful. Here's the roll. Make sure everybody signs the roll. How's it coming? What's that? Yeah, same stuff, right? Because we're given percentages of elements, and we need to... Did your shortcut work on that last one? It didn't work? Oh no, why not?
Because we were supposed to go to.
Moles instead of grams? Okay, yeah. Because the empirical formula is not the relationship between the masses and the elements, right?
Yeah.
Okay. How's it coming?
That's great.
Oh, that's good. Looks like you guys are getting along well. You getting it as well? See, this is an extra chair.
It's going to be 60. This one is chlorine, so it's going to be right down there.
All right, here's the question. What is our empirical formula? CXHYOZ, for example, right? Oh no, so CLZ. CLZ. Okay? True? That's what we're looking for. This means that we need to know the moles of each of these elements in this compound, right? So, did anybody get a number for the moles of carbon? Okay. Moles of hydrogen? 2.08. Moles of chlorine? Okay. So that means, well, let's see. Does anybody feel like they need help understanding where we got these values? Everybody okay with that? Then that means I can take this C 2.06, H 2.08, Cl 2.06, divide them all by 2.06. This looks like it's going to be CHO, right? Oh, sorry. Cl. Cl. All right, so there's our empirical formula. Anybody want to go over that? Any other aspect of it? We didn't even have to divide by anything because we were already in a 1-to-1-to-1 ratio, right? Well, maybe in a way we did divide. I don't know. Okay, so the next question is, if our molar mass for this compound is 290.83, what would be the molecular formula? What would be the molecular formula? All right. Can you tell me what the molecular formula for lindane is? What's the molecular formula? Screen. So, oh, writing. Keep the writing up high. Okay. So how much recording time do we get? 42 minutes? 40? Do you remember?
Somewhere between 40 and 42.
Okay.
Usually 42.
Too bad there's not a way to pause.
Yeah. Maybe there is, but I don't know.
I looked briefly and didn't see anything. Okay.
That's a little
Confused?
Yeah.
So we know
Yeah.
what? Empirical formula.
Yeah.
And we want to know the molecular formula. See how we've drawn this up here? I know that there's some multiplier between the empirical formula and the molecular formula. And that same multiplier exists between the, what does this stand for? What does that stand for? What does MM stand for? Molecular mass. So this must be empirical mass. So we have the empirical formula, so we can identify what the empirical mass is.
And that's 290?
What's 290? That's molecular mass, 290. But if we can identify the empirical mass, then we can identify this multiplier, and then we can use it here to get to the molecular formula.
So I'm doing the same thing I did on this equation to that.
The multiplier is the same. And so here we're trying to identify what this multiplier is, right? Do you understand where to get the empirical mass?
Yeah.
All right. Did anybody add these up? What is the empirical mass? 48? 48. The empirical mass is 48 grams per mole of that material if it was CHCl. All right. So from that information, we can identify this multiplier, right? 290 divided by the 48, 290.8316, divided by the 48 should be what? 6. 6. So that means our multiplier equals 6. That means our multiplier here also is 6. So then the molecular formula must be what? Very good. 666, right? Good. Okay, so actually, before we even started this problem, is there any of these that could have been, any other ones that could have been probable molecular masses? Or sorry, molecular formulas? No. So the only options were A or E, right? Okay, very good. Any questions about that? All right. So then, look at this nifty little laboratory setup. If I take a compound and I put it inside this container here, and I put oxygen into this container right there, I get the compound really hot and add this oxygen. What happens to an organic material if I get it hot in the presence of oxygen? It'll burn or combust, which is a fancy word for combine with oxygen chemically. All right? If I do that, then the material, especially if oxygen is continuously being added, the resulting combustive products will come through here and be forced down this direction and out. This is like a sandy material that will absorb water. This is a different kind of sandy material that will absorb